Lab 3, The Mass of a Black Hole, by Norwood Dennis. In this lab, I observed a star as it orbited a black hole of an unknown mass. The problem states that the position of the black hole is 3e to the 10th negative 3e to the 10th 0 meters. It also states the mass of the star, which is 1.9890 e to the 30th kilograms, and the time interval, which is 1 day, and in seconds that'd be 36400 seconds. It also includes a data set in the form of a CSV file that has x and y coordinates of the star at each time step in its orbit around the black hole. The problem also states that the only force acting on the star is the gravitational force of the black hole. Therefore, we can assume that the net force is equal to the force of gravity. We know that the equation for the force of gravity is the gravitational constant 6.7 e to the negative 11 times the product of the mass of the black hole and the mass of the star all over the radius of the orbit squared. Because we know all of the variables other than the mass of the black hole, we can rearrange the formula for the force of gravity to solve for the mass of the black hole, which would be equal to the net force times the radius of the Kissing circle, aka the orbit squared, divided by the product of the gravitational constant and the mass of the star. Using VPython code, I calculated the change in velocity and subsequently the change in momentum between each time step. From these momentum values, I was able to code for values for the parallel and perpendicular change in momentum over change in time. The parallel component is calculated by, we'll scroll down. The parallel component is calculated by the product of p hat, the direction of the direction vector that ensures that there it is. The direction vector that ensures that dp dt is parallel to the direction of motion, and the magnitude of dp dt, which is found by calculating the difference of the magnitudes of the initial and final momentum and dividing it by the change in time. The parallel component of the net force is equal to the parallel component of dp dt. The perpendicular component of dp dt right here is simply the total value of dp dt minus the parallel component of dp dt. And we know that the perpendicular component of the net force is equal to the perpendicular component of dp dt, which is the rate of change of momentum with respect to time. The star position variable is found by VPython from the index of the x and y coordinates in the CSV file given, and a trail is left by the star as it passes through these positions. Here, when we're solving for the mass of the black hole, in our equation, r, the radius of the orbit, is found by the difference of the star's initial position and the position of the black hole. Using the formula for the perpendicular component of net force, F net perpendicular equals mv squared over r, the velocity is solved for by taking the square root of the perpendicular component of the net force times the radius over the mass of the star, which we can see here. And then the mass of the black hole is then solved for using the equation the black hole mass equals the velocity squared times the radius over the gravitational constant. Since we have all the values for the parallel and perpendicular components of the net force, which is simply the force of gravity on the star by the black hole, we can model these components as their own vector arrows in the VIDLE module from Python. So if we go to Python and run the module, we can see that here we can see that the yellow arrow is the net force, the blue arrow is the perpendicular component of net force, which points towards the Kissing circle, the center of the Kissing circle, and the black arrow, which is the parallel component of the net force. What does it mean? What are the differences between the parallel and perpendicular components of Fnet and dp dt, also known as the rate of change of momentum with respect to time? The parallel component of Fnet is the force that causes a change in speed, whereas dp dt parallel is the rate of change of the parallel component of momentum. Fnet perpendicular is the force that points towards the center of this kissing circle and changes the object's trajectory, whereas dp dt perpendicular is the rate of change of the perpendicular component of momentum, i.e. the rate at which the trajectory is changing and in what direction. Simply put, Fnet is the vector sum of the force acting on a body, while dp dt is the observed effect of the net force acting on the body, which will change its speed and or trajectory depending on the values of the perpendicular and parallel components of the net force, respectively. What if our black hole was replaced by a new black hole of different mass, yet the positions of the orbiting star didn't change? It's basically asking, is it possible for the star to keep the same orbit around a black hole with a different mass? And I found that because the only, for this to be true, for the star to maintain its orbit, the black hole would have to be of the same mass, due to the fact that the mass of the black hole is what causes the radius of the orbit, and therefore the position of the star at each point in its orbit. This has been my Lab 3 presentation. Thank you.